So we've already talked about different kinds of frequency domain transfer functions. I want to specify it down to filters. Typically, a filter is a system with a frequency response that is designed to pass some frequencies and eliminate others. It filters them out. And when we go to specify a filter, a lot of times they're specified in terms of their magnitude frequency response. So we may have an area of frequency, say f sub p, and this is a low-pass example, and everything below f sub p, the gain should vary no more than some, say, delta h, just to give it a name, from some nominal value. And so the gain may do whatever it wants to as it passes through here, but the gain, when it gets up to a frequency of fs, which is the stop band edge, the gain after that is no more than, is attenuated by at least this amount. Okay, so the amount of attenuation and the locations and the amount of variation in the pass band, the amount of variation in the stop band, the amount of attenuation, those things are the main specifications of the filter. And one that's very important is the selectivity. So if we talk about the total amount of attenuation that we have, we're guaranteed that we have, I guess, at least this much attenuation between the pass band and the stop band, and the more of that, that adds to our challenge. The more attenuation we have to have, and the narrower the distance between, this is a so-called transition region, and the narrower the transition region is, and the more attenuation we want, the bigger the slope is as we come right outside the pass band. The steeper this has to be, that's called selectivity, okay? So a highly selective filter means that we have a lot of attenuation for frequencies that are fairly close together. And as we will see, the first thing that you would do to increase selectivity is to increase the order of the filter, the number of poles, the order of the denominator of the transfer function. So if we want it really steep and a lot of attenuation or a high selectivity filter, the first thing we're going to do is have higher and higher order of the filter. And we'll talk more about what that means in just a minute. After that, it's mostly about just what happens as we go close to this passband edge, and if you've been watching what we've talked about, that probably is ultimately going to have something to do with the Q of the poles that are associated with this. Well, let's just look at some of this. We've talked about, again, low-pass filters. The basic unit of the filter, so one way to build a filter is to put a cascade of different things. So we could put one second order filter here with a denominator, a numerator term, and this would be a so-called biquadratic section. It's got two poles. We could maybe have a second pair of complex conjugate poles here with a different set of things. And if it's an odd number of poles for the overall system, then we might have S plus another alpha. So the transfer function in that case would just be the product of all those things. And of course, when you multiply all this stuff out, in the example I've shown here, this would be a fifth order circuit because it's got S to the fifth power as the leading coefficient of all this thing. So this thing would have 5 poles, 2 of which are complex conjugate and 1 real pole. If we had an even number of poles, then they would all just usually be complex conjugate. Now, I say that they're complex conjugate, I guess I should have mentioned this, that for reasonably high selectivity, if we try to use real poles, if I tried to have a factorization out here where a couple of the poles are real, so that it would be convenient to write them as S plus alpha 1, S plus alpha 2, right? The real poles, as we know, I have a different place to draw this, but the real poles will have 2 breaks like this, and it's going to be hard to not cut this corner as we go through. So to increase the selectivity, we want to move these poles closer together where they can tuck into this corner more, And if you remember, moving the two poles together is exactly what we meant by increasing the Q. And then if we move them so that the poles would almost appear to meet, that would be, then as we increase the Q more, then we're going to get some peaking. And maybe that's just what we need, because the peaking would then allow us to fit this thing maximally as it goes through this thing. So typically, to increase selectivity, some of the poles are going to have somewhat higher Q, and most of the time, for most interesting filters, the poles will be complex conjugate. So that's why I sort of assumed that these were complex conjugate pole pairs. So while it is entirely possible, and we may see some ways that we could have built filters other than this cascade realization. A cascade realization, the input is applied to the first stage, the output of that becomes the input to the next. It's just like cascading over a waterfall. The output of this waterfall becomes the input to the next. That's what a cascade is. And this sort of a realization, then you just multiply the transfer functions together. Now, I just put ones in the numerator. If you remember, if we have constants in the numerator, then that makes this thing, if it's all poles like this, then that will be a low pass. And again, you can go through and see what happens at S equals very high frequencies. The S's start to drop off. When S is very small, then the constant terms out here would be the things that would become important. So this thing is going to be at low frequencies, it'll pass, and at high frequencies, it'll stop. So we've talked about that before. So the strategy we're typically going to use then is going to be, if we're designing a filter, is to first design the denominator, and design a low pass, and then there's various techniques. You can actually transform from a low pass to a high pass to a band pass and some others. But an alternate way is just, as you'll see, is just to kind of choose the numerator that you want. So how can we get the denominator of a transfer function that does what we want? I'm going to just show you some tricks here, and now I'm talking circuits, so I'm really on my most familiar ground here. The basic circuit element that is at the heart of every filter, we can start really with first order filters. If I wanted to start a first order filter, I can use an ideal op amp, or maybe a real op amp, in a configuration like this. Now this circuit is an integrator, and most of you probably know that from some class that you've taken. If this is the input, and you remember the ideal op amp assumptions, it says that these two voltages have to be equal if this is an ideal op amp. If this is at ground, then this has to be ground. The second ideal op amp assumption is that there's no current into the input. All right, so if this voltage is 0, then the current through this resistor is V sub I minus 0 over R. All right, so that's just V sub I over R is that current. If there's no current into the input to the op amp, then that current has to flow onto this capacitor. And in the time domain, it'll tell me that V out as a function of time equals the current. This is 0, so the V out equals minus 1 over C times the integral of the current, Vi of t over r dt. So this thing actually does the integral. Now the limits of the integral, I don't know what time t equals 0 was. Maybe, I guess what we really want it to be is some time when the capacitor had no charge, so the output voltage was 0. And then this thing just goes as long as t wants to run. So V out of t is just given by this integral. Oh, so it's an integrator. It integrates everything, the voltage on the left-hand plate, and the right-hand plate changes to satisfy this equation. So this is an integrator. We've been talking frequency domain. In the frequency domain, you can do this another way. What we typically say is, by the same analysis, if we have some Z1 and some Z2, then it can be shown that the output of this thing, this is the inverting op amp configuration, and V out in the frequency domain over Vn is equal to minus Z2 over Z1. In this example, Z2 is 1 over SC. in the Laplace domain, and Z1 is just my resistor R. So this thing has a gain, it's inverting, and it's minus 1 over SCR. So this is like an integrator. It's got a pole at the origin in the S-plane at S equals 0. So that's what an integrator does. Now, if you think about this in terms of stability, you would conclude something interesting about an integrator, or maybe it's not so interesting. But the fact is, it's got a pole at the origin. And for stability purposes, one of the definitions is that a system that has a pole anywhere other than the left half of the S-plane is unstable. This is right at the borderline, but it's on the j omega axis. That means by most definitions it's unstable. So what does that mean in our case? It means if you've got any input, like a DC input or something like that, and we just let this thing go, it's going to integrate out to infinity. In a practical matter, it would integrate until the op-amp can't be considered ideal anymore. So this thing has if it's got a bounded input, it can get an unbounded output. So that's one definition of instability, and this thing would have it. So that's an interesting fact. So how could we make it stable? Sometimes we call the way to make it stable a damped integrator, and sometimes we call it a low-pass filter. The damped integrator can be implemented by taking this same circuit and taking a fraction of the output and feeding it back around to the input. So now the total current, let me draw this slightly differently. The total current that flows through this branch now is, let me call this RD for damping. And the current that flows to the output, so I'm going to have in the frequency domain, V out equals minus 1 over SC times the current that flows into this thing. And the current is V sub I of S, that's supposed to be an S, V sub I of S over R plus V out over RD. Now this is interesting. This is in the form of a feedback thing. When you see an equation where you've got on the left-hand side you've got the output, and on the right-hand side you've got something that depends on the output, there's sort of a standard algebraic maneuver that I always like to do. We got V out times 1, and then there's a minus sign there, which is good because I want to be able to write plus for the next thing. And what I'm going to be able to write now is 1 over SC RD times V out, and then everything that's left on the right-hand side, 1 over SC R, where'd the SC go? SC times R times Vn. And so if I get the transfer function of this new thing, I take V out over Vs, we're just going to divide through by that. I get minus 1 over SCR divided by 1 plus SCRD. And you may have already noticed that we now have a pole in the left half of the S-plane. I can do various things with this. I can multiply it out, and I'm not sure there's any real benefit. SCR plus 1, it makes a different way of writing this, a minus sign, and the SCRD and the SCR, this thing becomes minus RD over R1. If we wanted to, we could think about this some more. This thing says that when S equals 0, that the gain of this thing is minus RD over R1, which is what you would get at DC, where the capacitor looks like an open circuit. So that's actually the DC gain. And now we can start recognizing this as a low-pass filter. This is in a standard form for a low-pass filter that's got a DC gain of K and 1 plus S over omega naught, where omega naught is the cutoff frequency of this filter, and omega naught is 1 over R sub RC, R sub D. This had a D in it, C. So the RD and the C form a pole, and instead of being at the origin in the left half plane, we've moved it from here, J omega, real part, we've moved it over to here into the left half plane where it belongs. And now we have a stable system. This is a low pass. Again, for low frequencies, this thing has a gain of minus RD over R1. At high frequencies, it drops off as a function of frequency. So this has a couple of things of use: K, omega, cutoff frequency, and then minus 20 dB per decade. All right, so we've seen these kind of low-pass filters. So this is how you can build a low-pass filter. You may have seen that before. Maybe that doesn't surprise you. Maybe there's no big deal about it. But I want to do something now that's going to move this up into the second order, and it works by analogy to what we just did. So what did I just do? I took an unstable circuit, the integrator, which put a pole on the j omega axis. I put some feedback from the output back around to the input, which provided damping, and moved the pole into the left half plane. Let me show you why that's going to be significant. Okay, so having talked about the effect of damping on the unstable integrator, now I want to go to second order, and by analogy I want to do the same sort of thing and create what's called a resonator. We've talked about the idea of the resonator before, the resonator being something that puts poles on the j omega axis. For example, we've seen the RC network here, or RL network, and we know that this thing puts poles on complex conjugate poles at plus and minus j omega naught, right, where omega naught equals 1 over the square root of LC. And this circuit is just like all the other things. If you put all the other resonators, if you put energy into the system, it has no damping. The energy will stay in the system forever. All right, so if we just close this loop, then this thing will energy will just stay in the system forever if we put any in there, and it'll oscillate as a sinusoid at a frequency omega. So we've seen all of that. And the thing that we want to do is to be able to add damping by put a resistor in here, and the resistance will lower the Q from infinity, and we'll get poles in the left half plane. And putting the resistor in series with this whole thing is going to be analogous to moving the poles into the left half plane. Now I want to show you how, by analogy to the active integrator and adding a resistor to add damping, that we can do the same thing with a second order resonator. So I got to be careful to draw this thing the way I want to, and then we'll see where we are. So the trick is we're going to put two integrators and an inverter in a feedback loop. So here's an ideal op-amp with a resistor R and a capacitor C, and I'm going to call the input to this one V2, and then I'm going to have the output of V2 come from the output of a second integrator. So V2 comes from another integrator, minus, plus to ground, capacitor. And this integrator, we have some flexibility, but I'm just going to do it with, again, an R and a C, and the two R's match and the two C's match. We don't have to do it that way, but that works. And the input variable to that I'm going to get from an inverter. So this is just a standard ideal op-amp inverter with two values of equal values of resistors here, so that if this voltage is called V1, then this voltage would be minus V1, and that's what I'm going to have as the input to this guy. All right, so this circuit, as we will see, and I'm going to derive this, is an integrator, and then we'll add damping and make it into a stable circuit. So let me write an equation first for V1. So V1 is the output of an integrator. So it's minus 1 over SC times the currents that enter into this thing. And I guess I want to have an input into this circuit, so let me add an input source, call it V sub I, and I'll give it a resistor R sub I. We'll put that up there. All right, so the currents that are flowing into this guy are V2 over R, for this R, and there is VI over R sub I, and I'm going to leave a little room here in case I'm going to add damping there later. And that is the expression we have so far. And now I want to write an expression for for what V2 is. So V2 is the output of this integrator. So V2 is minus 1 over SC times the inputs that are coming into that. The input to that is minus V1 over R, and that's the only input that it has. So that's what we have there. And what the strategy is here is I'm going to eliminate V2 from this thing and get an expression for V out in terms of just Vn and V1. So this is going to be minus 1 over SC, and then V2 is going to be, these two things will cancel, the minus signs will cancel. So here I'm going to have V, wait a minute, this says V out, that's the wrong thing, that's that's what I was calling V1. All right, so at any rate, over here, I'm substituting this whole thing in for that, and if I'm lucky, I will get this right. So it is V1 over S RC, and then that was all over R. So I guess I've got an R squared there. And then I've got V sub I over R sub I still, and again, I'm going to leave some room in case we want to do something else. All right, so here on the left-hand side we have V1, and we see that same term being on the right-hand side, and so we're going to use my feedback thing to eliminate this. And honestly, I don't need this equation anymore, so I'm going to get rid of it. I had already plugged it in up there. So I have V1 times 1. There's a minus sign here. When I bring this over to the other side, I'm going to get V1 onto 1 over S squared R squared C squared, if you will. I think that's right. And then there is another term, which is V sub I over SC. Whoops. V1 is still on the right-hand side. All right, so let's go back to the right-hand side. So this is the only stuff currently on the left-hand side. And so that's going to be, we brought this over, I've got V1 onto 1 over, and I think we've seen this enough, we know that it's SCR, the whole thing squared. All right, so that's my left-hand side. And what's left? What's left is on the right-hand side, minus 1 over SCR times V R sub I times V sub I. I think I'm finally there. And so what I want to find now is the transfer function. So what I get is that if V1 is the output and V sub I is the input, this thing goes down in the denominator. I get minus 1 over SCR1, minus 1 over SCRI is what this is, divided by, and I have 1 plus 1 over SCR quantity squared. So that's my result. Now, I could manipulate this around. I can multiply top and bottom by SCR squared and get this into another form if I want to, which I guess I do. And so this is going to leave me with SCR, the whole thing squared, plus 1. You see I'm leaving room for something here. And in the numerator, the SCR squareds are going to cancel, and I'm going to get a minus sign. I'm going to get an SC R over, R sub I. I think that's right. Okay. If we're real careful, well, so here's my main point here. As it's drawn right now, this circuit has a 0 where S equals minus 1 over R. So this thing has roots at plus or minus J omega naught, just as I promised, where omega naught equals 1 over RC. So it's set by the same frequencies as this integrator. And if we set R equal to S equal to J omega naught, then the denominator would go to 0. So this is our undamped circuit. Now the only thing I need to do now is to take this thing is a resonator, and if we gave it a chance, if we put energy into it, supposedly it'll oscillate at this frequency with constant amplitude. And so maybe that's interesting. If we were trying to build an oscillator, we could maybe try and do that. All right, I want to add a term here. I want to add damping, as we've seen before. So I'm just going to take this V1, I'm going to add this resistor, if I can reach up here far enough and do it, and add that back in as an additional input. So what that's going to do is, remember that this thing, V1, is the integral of the V2 current, the VI current, and now we've added one that's proportional to V sub I, and so V1, and so V1 over RD is added here. V1 over RD is added here, and that is going to add a V1 divided by 1 over SCRD in the middle here, and here. And then when I got from here to here by multiplying top and bottom by SCRD, so I'm going to get something that is R divided by RD onto SCR. And that's plus 1. And I think I have that right. We multiplied by SCR squared, so the SCR goes into the numerator and leaves the, just a minute here. First order. All right, hang on just a minute. Is this right? SCR squared. Oh yeah, there's an extra R in the numerator. I think this is correct. Now that needs to be matched up to our thing, and we can figure out what Q is. So the middle term is 1 over Q. I'll let you figure this one out because I want to make sure I get this right, over omega naught. And what we're going to find is then that the Q of the poles is the ratio of RD to R. Yeah, because omega naught is 1 over RC, and therefore RD over R is 1 over Q. So we're ready to roll there. So we have now figured out something very useful. We now know how to build a circuit that implements a pair of complex conjugate poles where we can set the frequency of the poles, and now we know how to adjust the Q, and we can vary RD to adjust the Q. The only thing that's left now is to start focusing on the numerator and the overall transfer function. If Vn is the input and V1 is the output, as we have here, we have a single pole at the origin and a pair of complex conjugate poles at plus and minus j omega naught. If you go back and review what all we talked about and look at the magnitude response of this thing, you will find that this thing is exactly my bandpass filter. So this is a bandpass with a center frequency at omega naught and a Q set by this. And basically, when S equals 1 over RC, these two terms will cancel, and the gain of this thing will be RD over R sub I. So this gain would be RD over R sub I. So we have everything we need to set all the parameters of a bandpass filter here. Okay? So I want to just kind of play with this a little bit. And what I really want to do is build one of these and have you build one of these and see what all you can do with it. One of the other things I can do is if V1 is a bandpass output, and I integrate that, so V1 over V sub I just kind of summarize this, is some sort of H0 times, not Q, H0 times S over omega naught divided by S over omega naught squared plus 1 over Q, S over omega naught plus 1, where with these correspondences we have this thing working. Now, if I integrate this thing and look at V2, it's the integral of this. Well, when you integrate something and multiply it by a minus sign, then the transfer function of that is going to be plus 1 over SCR. The 1 over SCR is the transfer function from here to here. There's an extra minus sign that turned this into a plus. If I multiply this transfer function, this one here is V1. This is V2 over minus V over V1 is equal to this. And so if I multiply to find this whole thing, I can get that V2 over Vn is, this thing is 1 over omega naught over S. That's what it is. It's omega naught over S, which means that's going to cancel this guy, which means when I multiply these out, it's going to be this. So V out, V2 over here as the output, or over here if you want to think of it that way, as a function of this, is now a low pass. So we have a circuit that simultaneously gives me a low pass and a band pass output. So we're really getting somewhere now. So I just wrote denominator because they have the same denominator. So this is real characteristic of lots of systems. We've seen them before, that the poles are a function of basically the feedback in the system or the system itself somehow, and the zeros have to do with how the signal is introduced into the circuit. I'm going to give you one more thing here that's based on the same principle. And then I'm going to try and turn you loose to build this thing. Let me show you a version of this circuit that we could do. And I'll let you derive it. This is my favorite filter. And it's basically just a variation on this same thing. If you have an op-amp, a set of operational amplifiers, you can get them that have 4 op-amps in a single integrated circuit package. And that's probably what you would want to use for this. And it's based on the same thing. So I'm going to first put, this is where my inverter is going to be. I'm going to put it here. And I'm going to put a resistor R1 around it. And the output of that, I'm going to integrate with something called R and C. And the output of that, I'll just draw it over here, another R and another C, minus, plus, ground. You'll need split power supplies for this, positive and negative. And then I'm going to take this signal and I'm going to put it through a little bit more complicated circuit than we saw before, but certainly nothing all that big of a deal. I'm just going to call this R3. It's more or less arbitrary. And this is where we're going to set the Q of the filter. So this maybe is something, maybe a controllable resistor. I'll call it R4 equals R3 divided by Q. R3 divided by Q is what this is supposed to say. And then I'm going to combine that as one of the other inputs into this thing. So this value and this value are going to be equal. And finally, I'm going to put my input in here. So I'm going to have this as my input. I'll call it R2. And its value is going to be R1 divided by H0. And I'm going to let you derive this as an exercise, I would say. But when you do, I claim that this is going to have the form of a high-pass transfer function. If we take this as the output over here, this is going to be a bandpass transfer function. This is going to be a low-pass transfer function. And it can be shown, maybe I should just do this. Here, I'll just write out the equations. So VH, and you watch me as I go. So I'm going to let omega naught equal 1 over RC, all right, with the two integrators. And I claim that VH equals minus VL, which was over there, minus VB over Q. So VB over Q. Oh, I left something out, didn't I? There we go. R1. Okay, so now this is starting to make sense. So this, I've drawn it wrong, you all. It's going to be all right. It's not going to hurt us. Not going to worry about it. So this is the one I'm going to call VB. This makes more sense. All right, so if this is VB, then this voltage must be minus VB times R3 over Q divided by R3. So this voltage must be VB over Q with a minus sign. So that's going to be here. And then that's going to get amplified. So these two resistors are equal, so this has a gain of 1. All right, I feel a little better. Then we're going to bring this one in, the input, and it's going to have H0 times VI. And the next equation says that VB is just the integral of VH minus omega naught over S times VH, which turns out to equal, don't have anything else for it yet. So the next one is going to be that VL, which is that output, is the integral of VB minus the integral of VB. But if we substitute these other things into here, then that thing has to equal omega naught over S quantity squared times VH. All right. I'm going to let you take the last few steps. If you do, it can be shown, and I'm going to let you show it, that you can write an overall transfer function of this thing that says that, that you can get three different outputs. So you can get VH over VI, and it's going to be of the form, which is a high-pass transfer function, so it's going to have an S over omega naught squared times one of these combinations of resistors times our denominator. So I'm going to let you derive this. S over omega naught plus 1 over Q. This was squared, S over omega naught plus 1, and that's my denominator. And the gain for this high-pass thing is set by, is just H0, where H0 was just set by these guys. The bandpass transfer function is available to you, and there may be a minus sign here, but it's got an H0 times S over omega naught to the first power times our same denominator, and then VL divided by V sub I is just H0 over our denominator. And then with all these outputs available, you can take a weighted sum of all three of these, and you can produce any numerator you want. And so this really allows you to implement every possible kind of filter. You can use this, again, with another stage to add up some other possibilities. You can implement weighted sums of these things in the numerator and get low pass, band pass, high pass, but also get notch, high pass notch, low pass notch, all pass filters, and probably anything else you wanted. So this is actually a very practical circuit. It works quite well. It has independent adjustment of the center frequency, the Q, and the pass band gain. So we're going to build some of these and have fun with them.